Chapter 4 of Think Python is more about the reasons why you would use functions rather than the technicalities of how to write functions themselves. He's written a package called Swampy, which works the same way as the turtle module, but you don't have to use the dot notation syntax. So you don't use Alex dot forward 100, you use forward bracket Alex comma 100. The setup for the function is fairly similar. As you can see, import the package using a slightly different syntax. This means you don't have to preface everything with turtle dot, turtle dot, turtle dot. You can just use them directly if you import them, but it has other repercussions. Here we see an example of the simplified syntax. So forward Bob, Bob's the name of the turtle that is created. FD is the shortcut for forward, LT for left, RT for right, and if we slide down a bit, we can see that here is a simple program for drawing a square. Forward, left, forward, left, forward, left, and then no left at the end here. And you should be familiar by now with this method of using a for loop with a range statement to do something 4 times. So on the next page we can see that we can apply that to draw a square by doing forward and then turning left. As he points out, we'll actually end up with an extra turn right at the end here after drawing the last side of the square. Here are a collection of exercises which I'm not going to ask you to do because they're similar enough to what you've already done in the interactive Python questions. First of all, we're asked to write a function square which takes a parameter t. This simply takes the for loop that we've created and puts it into a square function. The t parameter is the name of the turtle, which allows you to generalize this function so you can use it for any turtle, not just the one that you happen to be using at the moment. This is called encapsulation. You're encapsulating a chunk of code into a function so you gain all the benefits of having functions, as previously discussed. Then we're asked to add a second parameter, length, to the square function. This is generalization. It allows us to have one function which can be used by any turtle and can create squares of any size. In the third part, we are asked to change the function so that rather than just making 90-degree turns, it can make any turn you like, so just 45 degrees. We pass a new parameter n for an n-sided polygon, and we've also changed the name of the function from square to polygon to represent its new wider functionality. Finally, we're going to make use of our new polygon function to write a circle function, and takes the turtle t and the radius of the circle as its parameters. Now he works through the execution of these tasks. First of all, we have the definition of the square, which just takes the lines that we had before and wraps them in a function definition. The important part is this bit here, where rather than specifying which turtle we're using, like Bob, we are passing that as a parameter. So this function can now be used for Bob, but it can equally be used for Ray or any other turtle that we might want to use. Now we improve the function by adding a new parameter, length. So now rather than just drawing a standard sized square, we can pass 100 as the length of the side and then use that in the forward command. Now a further generalization, we add the parameter n, which is the number of sides. So here we call polygon on Bob with 7 sides and a side length of 70. If you think about it, it makes more sense to put the number of sides parameter before the length, because the number of sides of the polygon is a more important attribute than the length of the polygon. So if something is a square of side 30, it's a square before it is a square of side 30. It's not the length of the side that's the important thing, it's the fact that it's a square. It makes a very important point here that once you start to get a lot of parameters, it can be confusing as to which one means which. Was it a 70-sided polygon with a side length of 7, or the other way around? Python allows you to map parameters to arguments directly. So, as in at the top here, the parameter names are t, n, and length. You can specify those names when you call it and pass it the arguments n equals 7 for that n, and length equals 70 for this length. It has the added advantage that if you decide to swap the parameters round for any reason, or you just can't remember what order they go in, Python will pick them up correctly when it passes them to the polygon function. So it doesn't matter if you called it with polygon bob, length equals 70, n equals 7, the parameters will still be received correctly at this end. For this next bit of code, it's more talking about interface design than the maths itself. You don't need to understand the maths. Basically what it's doing is creating a new definition circle for turtle t with radius r, and it says that n should be 50, so it's a 50-sided polygon, which is an approximation of a circle, and the length is the length of the circumference divided by the number of sides, and then it just calls polygon and draws a 50-sided polygon of whatever length is needed for the sides. One limitation of the solution, as he says, is that for very big circles the line segments are too long, and for small circles you're drawing basically a pixel for each one. The question is then asked, who should decide what the value of n should be? Should it be figured out by the function, or should it be passed in by the user as a parameter? Which would give the user more control, but then they've got an extra parameter to worry about. So the question is, what is the cleanest interface that we can use? The interface of the function is a summary of how it is used or called. What are the parameters? What does the function do? What is the return value? So what goes in, what do you send to the function, and what do you get back? An interface is thought of as clean if it is as simple as possible, but no simpler. So take out everything that you can, anything that's not necessary, keep it inside the function, and only present to the user the essential minimum. In order to make this happen, he then creates a little bit of code here that figures out the number of sides that's most appropriate for this size of circle. The important thing in terms of interface design is when you call the circle function, you still don't have to worry about how many sides should be drawn. You just pass it the turtle and the radius, and the function deals with any extra work. This next part, you don't be looking at the code because it gets into a lot of grumpy maths. Basically what he's saying is he's defining an arc by making the turtle kind of walk a little bit, turn, walk a little bit, turn, and kind of draw the arc that way rather than doing it in steps. The point that he's making about refactoring is that quite often as you write the code, you find bits of the function could actually be pulled out and used as a function by themselves. So you'd extract them and then call them from within this function. You quite often find then that you can use that new bit of code that you've pulled out, you can use it somewhere else. So refactoring in computing is a lot like factorizing in maths, where if you have 2x squared and 6xy, you notice that you can extract 2 and the x from both of the terms, put it outside the bracket, and then you're only left with what's unique to each term inside the bracket. Similar kind of thing in computing. You extract certain parts of the functionality into their own function, and then you can call them individually. His final version of the program here, we have the polyline function. That's used inside the polygon function, and it's also used inside the arc function. Which means he can call arc inside the circle function, and it makes his circle very simple. He's just calling arc with an angle of 360 degrees. This process, rearranging a program to improve function interfaces, remember function interfaces is how you call the functions and what they're responsible for, and facilitating code reuse, so chopping bits of code out and putting them somewhere else so you can call them as a function, is called refactoring. In this case, we noticed that there was similar code in arc and polygon, so we factored it out into polyline. And he makes a really good point here. If we had planned ahead, we might have written polyline first and avoided refactoring. But often you don't know at the beginning of a project enough to design all the interfaces. Once you start coding, you understand the problem better. Sometimes refactoring is a sign that you've learned something. So usually you set off down the road of coding X, Y, and Z, and halfway through you realise that you could have done it better, you should have done it this way, and so you extract parts of the code. You don't actually change the functionality of the program. It still does, or should do, exactly what it did before. You're just making internal changes so that it does it more efficiently. Finally, he gives a very good overview of how at least small-scale coding is often done. You start off by writing a small program. Doesn't have any functions yet. You're just trying to see if you can get the thing to do what you want it to do. This is often the main nub, core, focus of the program. Once you've got that right, you then wrap it in a function and give it a name, so you can call it. Putting a name on something also enables you to read the program more easily. So your main program loop becomes 3 or 4 function call names, and you don't have to worry about how those functions do their job, so you're not wading through lots of code. You're only looking at maybe half a dozen lines of code, and that's the entire program, but it's just a load of function calls. Once you've got the function created, you then say, okay, well that does it for one, but what if I wanted to do it like this, or a bigger one, or more of them? Yeah, so you, instead of having one shop that does fruit and one shop that does fish and another shop that does meat, you have a supermarket that can do all of these different things, and you pass it a different parameter each time. You keep working through these steps until you've got a set of working functions, and then you look through your code to say, can I make my code cleaner? Can I make it more efficient? Can I extract things, put them in their own functions, stuff like that. You don't want to break the code, and this is where assert functions in Python can come in really handy, because you can assert that the output from a function, or the return value from a function, should be whatever your assert says it should be, and then when you've refactored the code and jiggled it around, you should get the same answers, so you can check that you really haven't broken anything. And just to round off, it puts in a little bit of information about docstrings. Docstring, as you can see here, it just comes after the header definition. It's in triple quotes, so you can run it over multiple lines if you like, and it just explains what the function does. Writing this kind of documentation is an important part of interface design. A well-designed interface should be simple to explain. If you're having a hard time explaining one of your functions, it could be a good sign that the interface could be improved. If you don't quite understand how people should call your function, you need to work on the function.